Section 3.1 in Chapter 3 is simply titled Force, and it is a discussion of the force of gravity, and the effect that it has on everything. And it's a fundamental equation or idea that we're going to use and build from that and look at other equations related to that. So let's begin by looking at the first equation for this chapter. And if we were all together in the classroom, what we would be doing today is we would be building our equation sheets. And this would be the first one that we would be working with. And it is simply equation 3.1. And it says force is equal to 9.8 times m, and m represents the mass of a body in kilograms. Okay, so when we're looking at this, we're going to be primarily, almost exclusively, talking in terms of SI units. So force is going to be the force that's acting on whatever it is that we're talking about, and of course that is in newtons, and the mass is in kilograms, and 9.8 is a constant, approximate constant that applies when objects are relatively close to the surface of the earth. So this is the force of gravity on objects that are within 30 kilometers of the surface of the earth. Now, beyond that, we don't really care of, more particulars about that. As engineers, technicians, technologists, we just need this fundamental relationship, and 9.8 is fine. And we don't need the units associated with it. We take the physicists and the theorists and the scientists, and they develop these things. They throw them over the wall, and as engineers, we're going to use that. He talks about all types of force. Basically, we're talking about overcoming the force of gravity. That relates to stretched springs or exploding dynamite. All these forces are expressed in terms of SI units, and that is given to us by equation 3.1. So he starts out, and if you go over to page 51, he says, calculate the approximate value of the force of gravity that acts on a mass of 12 kilograms. All right, so as we're looking at this, we have our fundamental equation that says force is equal to 9.8 times kilograms in mass. And for this particular situation, we have 12 kilograms given to us, and we want to calculate the force related to that. Very simple matter of plugging the value that we're given into this equation. So it's 9.8 times 12 kilograms, and I will write kilograms on there. All right, I multiply that out, and I get 117.6 newtons. That's the force that is applied to that object that has the mass of 12 kilograms. Now, he goes on to say, and this is something that we need to know as well, he says when using the English system of units, we have to make a distinction between the pound, okay, and something called the pound force. Pound force, okay, so the distinction between the pound and the pound force, okay, so pound is represented by this abbreviation, and pound force is LBF, okay? So a pound is a unit of mass, and it has an exact quantity given, and he gives that to us. This exact quantity of a pound in terms of mass is this, and I'll write it down. And he says that this is an exact equivalent. A pound is a unit of mass that's equal to that amount. Okay. He says, on the other hand, pound force is equal to 9.80665 times this number, and I won't write it all down again, but by this number, and that is an equal, equivalence that gives us pound force is equal to that amount. This is our conversion to newtons. And in this case, that comes out to be, if I put that in there, multiply it by 9.80665, approximately 4.48 newtons. So a pound force is approximately equal to that amount. All right, so let's work a problem with that and we'll be done with this section. He says, calculate the approximate value of the force of gravity that acts on a mass of 140 pounds. Okay, so this is a measure of mass, remember that, and express the result in newtons and in pound force. So to be able to do this, and I don't have access to show you this, but he says using conversion charts, and he says in our appendix there's a conversion chart located here, and if we look that up and we go through that process that we went through in the first chapter, it says that 140 pounds divided by 2.205, and 2.2 is kind of always the number I use when I'm thinking about doing that conversion. And anyway, and sometimes even just 2, right, to get an approximation to go from pounds to kilograms. But anyway, 140 pounds divided by the conversion factor of 2.205 gives us 63.5 kilograms. Okay, now once we have this in kilograms, we can go back to our original equation 3.1, and we can place that number 63.5 in that equation and then do the multiplication. And then when we do that, 63.5 times 9.8 gives us 622.3 newtons. Now, once we have that in newtons, we can use the conversion factor that we just talked about. So we can take 622.3 newtons, and we can multiply it by our conversion factor. Excuse me, I said multiply. That is not what we're doing. We're going to divide, aren't we? And to divide by that conversion factor, and that conversion factor we determined to be 4.448, right up above there in the example 3.1 that we talked about. And when we do that, we come out with 139.9 pound force, or lbf, okay? And this is the English equivalent measure of force, okay? Conversion, English, and this gives us this equivalent, taking newtons and converting it to an English equivalent, okay? And, he says, note that the force of gravity, 139.9 pound force, is almost exactly equal to the mass of 140 pounds. However, although the numbers are nearly the same, a force of 140 pound-foot is entirely different from a mass of 140 pounds, okay? One is a measure of mass, the other is a measure of force, okay? So that's section 3.1, and we'll look at a few more examples of this toward the end of this chapter, but that gets us going. And if I were you and I was working through this chapter, I'd go ahead and start making a formula sheet. Everything in this book is really equation based. So, get you a list of relevant equations, and they're given to us in order in the text. And the first one for us would be this equation 3.1 that says force in newtons is equal to 9.8 times the mass in kilograms. And we'd label that as 3.1, and that would get us going. All right, 3.1 is done.